Welcome back, students. Welcome to the video lecture in Signal and Systems. In the previous lecture, we have covered what is state space, and we have seen three vectors that defines a MIMO type of system, that is multiple input and multiple output type of system, that the system is having m inputs from U1 to UM, and the system is characterized by n state variables, that is from x1, x2 to xn, and the system will produce p outputs from y1 to yp. Okay, there you have seen three vectors, that is state vector, the input vector, and the output vector. Today we will derive a model for the system, that is state space model. So starting with the state space model, let us first see that the state vector representing current state is equal to xt. तो जो भी हमारा मल्टीपल इनपुट मल्टीपल आउटपुट टाइप ऑफ सिस्टम है, it is characterized by its state. So to determine the output of the system, we require the knowledge of these state at the current time t. Okay, so state vector हम define कर रहे हैं from x1 to xn. Here we can also write it as, actually all these things are in time domain, so for simplification we will write this vector again as x1, x2 to xn, where these are time dependent vectors. Okay, and they depend upon the value of time, that is t. So our model here will have two type of equation. The number one equations that we gonna deal are state equations. So starting with state equations. So state equation describes continuous rate of change of state with respect to xt, that is a current state, and the input ut. So यहाँ पे जो मॉडल डिराइव होगा, वहाँ पे पहली जो इक्वेशंस होंगी वो होंगी स्टेट की इक्वेशंस, जो डिफाइन करेगी स्टेट के रेट ऑफ चेंज को, एंड दैट रेट ऑफ चेंज यानी कि dx by dt डिपेंड्स अपॉन current state xt and input of the system, that is ut. So I can write it as dx by dt is equal to a function of xt and ut. That is our state equation which defines the behavior of a state. Okay, तो जो भी state का behavior है, यानी कि उसमें how much there is a change, that is defined by dx by dt. Okay, and the other type of equations is the output equations. So the output equation will change or will be according to the current state xt of the system and our input and ut. Okay, so जो हमारी आउटपुट इक्वेशंस होंगी, दे आर डिपेंडेंट ऑन द करंट स्टेट, व्हाट विल बी द करंट स्टेट ऑफ द सिस्टम एट t is equal at time t, and what will be the output. Okay, so considering our first equation, that is dx by dt, this is our first equation and this is our second equation. We will derive these equations first. Okay, so considering the first equation, dx by dt is equal to f function of xt and ut, we will write it as that dx1 by dt is equal to a11 x1 plus a12 x2 plus up to n state variables. So all the state variables उसमें include हो जाएंगे up to a1n xn. ओके, प्लस यहाँ पे जो हमारे पास आउट इनपुट्स हैं वी विल कंसिडर देम. सो b11 u1 प्लस b12 u2 प्लस b1n u actually it is m, because we are having m number of inputs. So your first equation will look like this. Okay, so dx1 by dt is equal to a11 x1 plus a12 x2 plus up to a1n x1 plus b11 u1 plus b12 u2 plus up to b1m um. Okay, in the same way we can write for other equations as dx2 by dt. सो ऐसा हमें हर एक इक्वेशन के लिए लिखना है. तो आई कैन राइट लाइक a21 x1 प्लस a22 x2 प्लस a2n xn प्लस b21 u1 प्लस b22 u2 प्लस b2m um. Okay, so in this way I can write for the second state vector that what will be the change in the second state vector. Okay, and likewise we can write for the other equations, and I am writing for the nth state vector as dxn by dt is equal to a n1 x1 plus a n2 x2 plus up to a n xn plus b n1 u1 plus b n2 u2 plus up to b n M U M. Okay, so likewise we have written the state equations for each of our state variable. So whatever will be the change in our state variable will be determined through these state equations. Okay, so combining all the state equations and using these equation as in the matrix form, we can write it as a vector matrix here, which is x1 dot that describes the differentiation part, x2 dot up to xn dot. This is equal to, here we will write our coefficients of the equation, that are a11, a12 up to a1n, a21, a22, a2n, an1, an2 to an n. Okay, so likewise you have written all the coefficients here, and when it is multiplied by the state vector x1, x2 up to xn, plus we can write for our coefficients that are with our input vector. So I can write it as b11, b12 up to b1 b21, b22, b2m, here b n1, here b n2, and here I can write b n m, and when it is multiplied by u1, u2 up to u m. So in this form I have derived a model for our state equation first. Okay, so till then you have seen that rate of change of the state vector xt is a function of xtut. So we have defined our state equation as dx1 by dt is equal to a11 x1, and likewise we have defined all the n state equations. So in this format I have come to a conclusion that this vector, which I can represent by x dot is equal to, this matrix is, I can call it A matrix multiplied by our state vector x plus this matrix, I can call it as B matrix multiplied by our vector u. Okay, so right now I can write it as with t. As discussed before, everything that we are writing is in time domain, so I can write it as, also if I don't want you to write in with t, then I could simply write it as x dot is equal to ax plus bu, where these two matrix, the matrix A is defined as system matrix, okay, and this system matrix defines how current state affects the rate of change of state vector, okay, that is dx by dt. So how the rate of change of the state vector is affected by, it can be analyzed by our system matrix A, okay, and I can write B matrix here is equal to input matrix, okay, because it is associated with input vector, so it is input matrix, okay. So input matrix defines effect of input on state change. So how the state will be affected by the input can be defined by this matrix B over here, okay. So the equation that you can see here, this equation we termed as, combinedly we termed as state equation, okay. So this is what we called as state equation, okay. Now if we see that yt is also a function of xt and ut, and whatever will be the state according to the change in state will defines our yt. So I can write equations for our yt as y1 is equal to c1 1 x1 plus, I'm writing directly to c1n xn plus, here we have another coefficient as d 1 1 u1 plus, and I'm directly writing 2 d 1 m um. Okay, and in this way I can write for all the outputs, that is pth output. So for pth output I can write c n1 x1 plus c n xn plus d p1 u1 plus d p m u m. Okay, and in this way I can write them in the form of a vector like we have done in our previous case. So from y1 y2 up to yp I can write it as in the brackets we have our first matrix, that is c11 c12 up to c1n, and here I'm writing the state vector. So here we have one matrix, that is the matrix C, okay, plus here we have another matrix, that is D11, and in the multiplication we are having the input vector u1 u2 to um. So in this way I have defined a equation in the matrix form for output, and I will call it as D. So the equation I can write it as y is equal to C matrix multiplied by our state vector plus D matrix multiplied by our U. I can write it in time domain as this, or simply I can write it as that y is equal to cx plus du, okay, where the matrix C is called as our output matrix, this output matrix defines the relation between system state and system output. So output matrix defines relation between system state and system output. Okay, and we have another matrix here called as D matrix. It is called as transition matrix or feed forward matrix. Okay, or transition matrix. Okay, this transition matrix defines or allows the system input to affect the system output directly. Okay, so D allows inputs to affect output directly. So in this way we have defined two equations for our state model. The equation written here, that is y is equal to cx plus du, this equation is called as output equation. Okay, so now we have developed two equations, and according to these two equations we will develop the system model. So for system model you can see the first equation, that is x dot is equal to ax plus bu. So I can model this thing as x dot, if this is the x dot, then this x dot is equal to, can place a summer here, and this is our signal u, the input to the system, which when multiplied by b. Okay, so if it is input u and I will multiply the input by b, then I will have bu here. This is a summer block. Okay, so it will sum, it will be used as a sum here, and I require ax more. So if I integrate this d by dt, I will get x. So I'll integrate and get x here, and if I multiplied this x signal taken from here with a, and add to bu, then I'll have this type of system block representation for ax plus bu. That is for our state equation. Now the other equation says y is equal to cx plus du. Okay, so first of all we are having a x here, so if I multiply it with c and add it to du, so where is u? We are having u here, so I'll take u from here and multiplied the same with D as here, and if I add these two signals, then we will have our output as U. Sorry, output as Y. Okay, so in this way we have developed the state model for the two equations, that is ax plus bu, and the other one is y is equal to cx plus du. So this is all for today's video lecture. I hope you will enjoy this video lecture, and thank you very much.